first researcher on the planet to publish paper about PFAS chemicals. Amazing biography with more than 1,500 papers, finishing that's 130. It's a quite unique opportunity for all of us to have such a guest at the Faculty of Chemistry. He received many awards. He established also a science court in Canada, which is also very interesting. Together he will tell us, well, the first lecture will be about the PFAS analysis, and the second one will be about environmental forensics. So, what is also important is that Professor Giesy is a emeritus distinguished professor and former Canada Research Chair in environmental toxicology, but also member of the National Academy of Sciences of Canada and fellow of the Royal Society of Canada. And his current positions are emeritus distinguished professor of integrative biology, Michigan State University, and distinguished visiting professor and member graduate faculty at the Baylor University, where our friend George Gold is also professor in your course. So, John, thank you so much again for being together with us in this bonus summer school. I know that you have something special. I believe that all of them are here. So, Maro, Branka, Chuka, Kiki, Nata, please. Yeah.
Everybody. Okay. Thank you, sir. Thank you. So before I start, I have some important business. So I'm a professor. I've been a professor for 50 years, so I'm an old guy. So I know how it works. So this guy over here is the leader, right? He's the one with all the crazy ideas and the hard work to get all the money and all these things. But I know he needs executive officers, right, to get those things to come to reality. So for that team, I have some things here. So I'm going to call some people up. I'll start with Alexandra. For you.
Thank you.
You're welcome. Use it in good health. Branka. There you go. Now, I also know how the world works, so they all get the same thing. So there'll be no fighting or trading later, all right? I just want to make sure. Okay, Christina. Also for you.
Thank you.
Use it in good health.
Thank you.
And last but not least, Maria. Okay. So these are from my province. So I live in Saskatchewan. I know it's hard to say. We always tell people it's the easiest to draw because it's a rectangle, perfect lines, but hardest to say. So the other Christina, I have something for you. It takes a little bit of explanation. I hope you like it.
Very much, thank you.
So my daughter's a little bit older than Christina, but she loves these plush toys. Everywhere we go, she's getting one from everywhere, different things. But this is a special one. This is a moose, okay? And we have these animals in my yard where I live. So I live at the edge of the world. I live about 500 kilometers north of the United States. So I live, and that's about a third of the way up my province. So it's a big province, and there are only about 1 million people. And so in my yard, we have many deer, maybe up to 100 sometimes, 2 species of deer. We have antelope, we have coyotes, we have wolves, and bears, and lots of things just in my yard around my house. So anyway, that's the moose. Okay, Natalie. Now there may be some fighting over these plush toys because they're not the same. You know what this one is? It's a beaver. Okay, so this is the symbol of Canada, is the beaver. And Canada was settled by Europeans. When Europeans first came to Canada, it was to get the pelt, get the fur from the beaver. Because in those days, in the 1700s, very popular here in Europe were these big tall hats, right? And they made from beaver, from the pelt of the beaver. So there you go.
Thank you.
His name is Bucky.
Bucky.
And the moose already also has a name. His name is Mac. Okay, so zum Arbeit, to work. For some of the assistants, I've left a list of papers on perfluorinated compounds. If maybe we could make a few copies for people to have tomorrow. If you want to then get them, you can just ask for them from me. I'll have my computer tomorrow, bring a flash drive, I'll copy them over for you, so you don't have to pay. A lot of them are open access and free, but some the publisher wants you to pay. I don't want you to pay anything. Okay, how do I go back? Okay, so Labware has asked me to do a few things. Today we have really two lectures, one on analyses, instrumental analyses. For that I have standard operating procedures. I've given a list. Tonight I'm going to copy all of them onto flash drives. So everything I talk about, the details of things, are written there, and I have them as a PDF and also as a Word file. So I will give all of those to you, and then you can, I think they all say copyright on them, but that's what we're just supposed to do. But it doesn't matter, you can use them. Okay? So I'll bring all of those. So really all the details I talk about today, you can go there and look up later. So, just a little background. I'm not going to spend much time on this because we've been talking about it now for quite a while. But one of the key things to remember about these compounds is that they can be either straight chain or branched. The fluorine-carbon bond is very strong, 110 kilocalories per mole. There are no chemical bonds in nature that are that strong, and there are really no processes in nature that will break that bond. So it's a very strong bond, and that's why we call them forever chemicals. So these chemicals have been made since the early 1950s. Lots have been made. In a minute I'll tell you more, but we're talking about thousands of chemicals, not just one or two. The first one that I discovered was PFAS, perfluoroalkyl sulfonate, which was used in large amounts, and also PFOA, which is a carboxylate. Both are 8, well, PFOA is an 8 carbon, because it's a carboxylate. PFOA is 9 carbons, but PFOS is an 8-chain carbon. So there are really two ways that these are made, and this is important because depending on who made it, at least in North America, those are persons that are responsible for what's in the environment, so they might have to pay. So later I'll talk about forensics, how we figure out sources of chemicals in the environment, and really what they mean or do. But the first one is called electrochemical fluoridation. This is the process that was used by 3M Company in North America, and it's the process used by Daikin in Japan, and it's it's the process used mostly in China. So a lot of the chemicals that are in the environment were formed by this process. So some of the key things about this process is it makes straight chain and branched products, but the way it works is we basically take hydrofluoric acid and put it in with various precursors to make the perfluorinated compounds. Because of this process, if you can imagine, we sort of mix all these things together and then just zap it with a lightning, basically lightning. Tesla would be happy, he would like it. But we put a lot of electricity in, and in this process it forms the key chemicals that we're trying to produce, but it also produces a lot of other things, okay? So it's a non-specific process. And the chemicals that we want, we sort of pick out later. So this is electrochemical fluoridation. This was what was used by 3M, and it's about 70% straight chain and about 30% branched. Straight chain and branched is important because of toxicity. There's a big difference. And in fact, these chemicals are very effective at, as insecticides, particularly for the cockroach. And it turns out, generally with chemicals, branched chemicals are more potent than long chain because of their volume. If they're branched, they have a larger molecular volume. But in this case, it's the straight chain that are more toxic to cockroaches and that were separated and used as an insecticide. The other process that makes them is telomerization. The key thing here is it is a controlled process, and we, depending on what precursors we use to make this, we get different products, but we always get only that product. This process does not make a wide range of chemicals. I see a few people making notes. Again, this lecture I give to everybody. I have a PDF. I'll give it to you so you can go back and look at it and use it, and I'll do that today. And if people miss anything, just you can write to me later and I'll send it. So anyway, this is all, everything that's here you can have. Okay, so the current status of PFCs, since 2009, several of these, PFOA and PFOS, have been regulated for virtual elimination in the world under the Stockholm Convention. So I work very, very closely with the United States Environmental Protection Agency and also with my ministry in Canada. In Canada, we banned them all in 2006. So we were really the first country to ban some of those chemicals. Yeah, so I have some information here about the market size, but the key thing is it's a lot. We're not making small amounts of some of these products. Later, when we talk about a risk assessment, I'll talk again about risks and benefits. And one of the key things of that is really how much is produced. So there can be some chemicals that are very, very potent and have potential adverse effects in the environment. But if only small amounts are made, they're not a big risk. If they're used in a confined way so they don't really get into the environment except maybe by accidents, again, they're not as much of a risk. But if they're made in large quantities and they are persistent and they are accumulative and have toxic potency, then they're a problem. And these chemicals that we're talking about today meet those criteria. Okay? They're very, very persistent. Now, they don't bioaccumulate like organochlorines. So most organochlorines are neutral molecules, and they are partitioned into lipid, into fat. They don't want to be in water. They would rather be in an organic substrate, like fat in an animal. These chemicals don't do that. They are ionic. They would love to be in water. They're very good surfactants. And they don't accumulate in lipid. They bind to proteins. So they behave very, very differently in the environment. And the matrix that we'll find them in for our analytical chemistry depends on that. What else of that dashboard? This is just some information from the EPA. So if you have this in front of you, you can go to these websites and they'll have everything available up that's most recent within the EPA. Do it quick before the EPA gets closed. I've heard this new guy in the United States is trying to close the EPA. So do it quick. I make a joke, but it's a serious problem in America. So anyway, you can go to these websites and they're updated and they have all of the most recent information. And they have literally thousands and thousands of references and papers and things. So you can go to all of these and get the information. One of the most recent ones, this one was like 2003, they're doing a whole country survey in the United States of public drinking water supplies. And there are rules now for what's allowed in drinking water in the United States. And as you can imagine, these chemicals are ubiquitous in the environment. They're really everywhere. And they're found in most drinking water. And the other key thing for analysis, which we're talking about today, is almost every year or 2 years, governments are lowering the standard for what's allowed in drinking water or in environmental matrices. It's going down, 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 down. And in fact, now some legislation is written such that it's essentially none is allowed. Okay, if it's detected, that's a problem. So that means our analytical chemistry is really going to be determining what the regulations are. Because the way the law is written is if you detect it, it's a problem. So if we lower our detection limits, that's decreasing the amount that's allowed in the environment. So this was really my doing. I met with our Minister of the Environment, and we decided on July 1st, 2006 to ban all these chemicals in my country, in Canada. So some more information here on these things. So, analyses, that's the key discussion for today. There are a large number of these compounds. I'm going to talk about PFOA and PFOS as examples, but there are many, many PFAS in the environment. Remember I told you electrochemical fluoridation makes a lot of things, and in addition to that, there are many products that are being made. And there's contamination coming from many things. But for us, for analysis, one of the problems is contamination from storage bottles. So remember, we're now talking about part per quadrillion, part per quintillion, 10 to the minus 18th, one molecule in 10 to the 18th molecules. So we're looking at really small amounts. You can't see it, you can't smell it, you can't taste it, but it's still there. And one of the problems of doing those low-level measurements is contamination. And that contamination can come from storage bottles, plastic bottles. A lot of people like to use Teflon because they think it's inert. Well, Teflon's made of fluorochemicals. So Teflon's the last thing you want to put your sample in. So a lot of things we might have done for metals or for PCBs or for DDT or other things historically don't apply anymore. Labware, pipettes, all kinds of things are contaminated with these compounds. But a key one that I'll talk more about is the instrumentation. So inside your instrument, there's a lot of Teflon and other fluorochemicals, fuels, seals, in gas chromatographs, in LCs, have these chemicals in them. They're there because they're very resistant to oxidation, hydrolysis, microbial degradation, or chemical reactions. They're basically inert. But they will leach out small amounts of these chemicals. So early on, a lot of the data that was being generated, not our early papers, because I think we knew what we were doing, but after we published those first couple papers, scientists all over the world got excited and said, whoa, here's something new, we'll jump on it. But they didn't really know what they were doing. And in many cases, they used inappropriate instrumentation, but they didn't know to check a lot of these things. So a lot of those early samples from marine systems, from water, anything more than about 5 or 6 years old is suspect, because the instruments themselves were contributing. I'll show you how to deal with that, how to eliminate that problem, so you won't have that problem, but early on that was a big problem. Initially, there were no standards, none, zero. And then for a long time, there were no isotopically mass labeled standards. And that's what we need to do for isotope dilution, which is the technique I'm going to teach you how to do. So if you don't have a standard for it, it's difficult to do the analysis. You can do it and you can get a semi-quantitative result, but for publication, that's going to be difficult. One of the things I'm going to talk to you about today is methods for measuring organically bound fluorine. Now, I've come again with ifs, and I'm an honest guy, right? I always tell the truth. I have to be honest and tell you, this was not my idea. This was your professor's idea. Good idea. So I have some here. What was I going to ask you about? I can't remember. Anyway, I've got them here. So I'll be asking a few questions. So a couple other things here. You have to worry about. Oh, I know what I was going to tell you about. Okay. Organically bound fluorine. Why would you measure total organically bound fluorine? Going once? Going twice? So we like to do what we call mass balance analysis. So if I do an analysis, and I told you the other day, chemists find what they look for. If you're not looking for it, you may not find it. One of the things I'll tell you about here is ways to measure the total amount of organically bound fluorine. And then you can add up all the mass that you've analyzed, all that you've identified and quantified to see if there are other things there. We've been doing this with brominated compounds and fluorinated compounds as well. But for some of them, like brominated compounds, even though a lot of them are flame retardants, right, in samples from the environment, we routinely will account for 1% of the organically bound bromine. So there are a lot of other things there. Some are natural products, some are toxic, some are not, but you need to know what they are. Okay, well, nobody gets that one, so I'm going to keep it right there. Okay, there are a lot of matrix effects, so I'm going to teach you about something called matrix matched quantification, because a matrix, what the sample's in, can enhance or depress the signal in the instrument. And so you need to know that. If you do what's called a matrix match or an internal standard or doped sample, you can eliminate that problem. So that's probably the best way to do things. Instrumentation is expensive. In my laboratory, we have a GC Orbitrap, we have LC Orbitrap, we have triple quadrupole tandem mass spec, we have MSD LC and MSD GC. The Orbitraps, I get a special deal from the company, from Analytical. I wrote an agreement with them that they can market the software that I've written for the instruments, and they give it to me for half price. But each one of those costs about $1 million Canadian dollars. I'm not sure what it would be in dinars. A lot, a lot more. I don't know who here has access to that instrumentation, but it's expensive to get into this business. Okay, highly trained personnel. I can't teach you everything you need to know today. So you need to work with people that are experienced, and it takes a long time, really, to get up to speed. One of the things for identifying novel compounds is a lack of libraries. One of the other things Thermo got from me was I gave them our libraries of retention times and parent ions and transition products for a whole range of chemicals. And they market that. And they gave, I didn't want the money, I didn't need money, I wanted the instruments for the best price I could get. So I got a half price for my instruments. Plus they gave me maintenance contracts in perpetuity for forever, which costs a number of thousands of dollars every year. And then the final thing here is I'll tell you more about these chemicals, is they're fatty acid analogs. And that's why they're difficult to extract from tissues, because they act just like a lot of the chemicals that are natural products, say in blood or liver sample or kidney sample that you might be analyzing. So that makes it difficult to extract them, so I'll show you a way to do that. Otherwise, if you use sort of standard, historically used extraction techniques, you'll get all of those interfering compounds. And I'll tell you a story about some blood analyses where that was a real problem. So the questions we'll talk about today is I'll talk about some methods for extraction and quantification of organically organofluorine compounds. Some about separation from water, sediment, soil, biota, and quantification by ultra-high resolution mass spectrometry. You can't use a normal mass spectrometer for this analysis. If you have a unit mass instrument or an MSD, forget it, you can't do these analyses. We'll talk about these methods for total organically bound fluorine and some mass balance examples. Here are some of the chemicals of interest. I'm just going to talk about PFOA and PFOS, but as I said, there are a lot of other chemicals in the environment. Here are the structures of the ones I'm going to talk about. In particular, here I've just as an example, I've given a linear, but these chemicals also come as branched. They'll have the same mass if it's straight chain or branched, but they'll have different fragmentation patterns. And you need to know that to be able to quantify these. Let's see. So people were trying to analyze for these chemicals. They tried GC, gas chromatography. These terminal degradation products, PFOS and PFOA, have a very, very low vapor pressure, and they're not neutral molecules, they're ionized. So really, gas chromatography is a completely inappropriate method. So if you're thinking of trying to measure these by GC, forget it. it won't work. It really has to be LC. We do derivatizations to be able to extract these and isolate them from other products. I don't know how many people have done derivatizations. A few, right? They can be messy, they can be difficult, and when you do it, you can often derivaterize a whole bunch of things that you're not interested in. So there's some tricks to the trade to doing that. So HPLC is really the way to go. Fluorescence detection will work, but only on an industrial scale. So if you're screening product and you want to know how pure your product is, you can do that. But the sensitivity for fluorescence detection is not sufficient for environmental samples. You can use NMR. When we first published our papers, a lot of people didn't have the appropriate instrumentation, but they did have NMR in their institute. You can do analyses of these compounds by 4019 NMR, but it's not sensitive enough for environmental samples. Remember, we're talking about part per billion, part per trillion, part per quadrillion, part per quintillion. Very, very, very low detection limits. So, the current methods that we've developed for tissues, which is primarily what a lot of people are interested in, you'd like to know what's in the human or wildlife, uses ion pairing. And I'll show you how we do that. With separation by HPLC and quantification by negative ion electrospray, high resolution mass spectrometry. You can use tandem, but you need to be able to use, you have to get M1 and M2 data. You have to get the parent ion, and you have to be able to break the molecules apart and get the secondary or transition ions to be able to identify them. So the sensitivity in blood plasma now for us is about 5 nanograms per milliliter, which is well below what the standards for human blood are. So we can do that. I would suggest that you use Orbitrap. Our instrument has a resolution of about 2 parts per million. That will give you 6 orders of magnitude, and we use 1 order of magnitude for rounding. So I always get 1 less than what the instrument will give me. So that means about 5 orders of 5 decimal places. And that's enough to give you an accurate mass. And with an accurate mass, you can always predict the elemental content of your parent. So you know what elements are there. But you don't know how they're arranged. You don't know what the structure is. But a key thing for doing an analysis and being able to separate these compounds or to be able to identify them, you really do need to have an accurate mass. You can do that with an Orbitrap. It's Thermo's name for things. In particular, I would suggest the Q Exacted is the instrument that you'd like to have. So if the government calls you and says, hey, you want me to do some of this stuff, you say, I don't have the right instrument, that's the one to get. Okay, let's see, we talked about ion pairing. When we first discovered these chemicals, I was going to lots of scientific meetings, but including something called the Pittsburgh Conference, which is a huge conference, mostly of instrumentation, but all the suppliers are there. But they're, pretty big meetings. There are like 5,000 people there. And you can go and talk to people. And right about that time is when electrospray mass spectrometry was being developed. I got my PhD at Michigan State University, and the people I was working with there, we were developing mass spectrometry. Chris Inke was one of the very first people. I was working with him. I was working with Matt Savick, and we were developing those techniques. Later, I was brought in by Otto Hutzinger, who was the world's premier dioxin chemist, and learned my trade from Otto. For dioxins, you use a magnetic sector instrument, and these are all electrospray tandem mass spectrometry. These can be really compound specific, and I told you that the extraction is complicated. So I'll give you just a little idea of how this would work, and then the details are in those SOPs that you can have. And then you follow those step by step by step. But basically, for water, what we would do is we would spike with an internal standard. Remember, we're going to do isotope dilution, so you would have to have a standard that's mass labeled. The mass of PFAS, for instance, is 500. The ion in negative ion mode, which is what we want to do, would be 499. And so you'd want to have one that is labeled with tritium, for instance, to give different masses. Be careful with the contamination. We have a Canadian company that you can buy things from called Cambridge. I don't work for them. I don't get any money from what they sell. But they work closely with me. So when I tell them we need standards for something, we've been doing a lot recently with organobromine compounds and azo dyes and a lot of things. And there are hundreds of azo dyes, all your blue jeans and all these things. And there were no standards. So they worked with me to produce the standards we need. I can rely on them to make accurate standards and pure standards. I don't know who might be making them here in Europe, but I would be very, very skeptical and make sure you've demonstrated. Because when you're working at part per quadrillion levels, if your standard is slightly contaminated, so normally when you buy standards, it'll say it's 98% pure, 99%. Well, I mean, that'll just blow your analysis off so much that it wouldn't be anything close. So you need to be careful. We do spike and recoveries of internal standards. A lot of the papers on that list give you details. There's one by me with one of my students, Jonathan Nail. It goes through this whole process of how to do matrix matched analyses, and we checked a whole lot of things as to whether they were straight chain or branched, or whether they were contaminated or not. And that's all detailed in that paper. But in general, we would use a solid phase extraction. The thing about ultra high, so I'm a mass spectroscopist, ultra high resolution mass spectrometry, the key is we do our selectivity, we do our separations on the mass, not on the LC. Okay, so you have pretty crummy LC. You don't need to separate things that well, because we're going to do it on the other end with the mass selectivity. So, you need decent LC. If you have micro LC, that's helpful, but that's expensive and generally you don't often have. But we would use a C18 or a wax column, and then just dilute that with methanol. So it's pretty simple. It can be pretty dirty because, again, we're going to clean that up in the mass spectrometer. You don't want to put a lot of crap in your mass spectrometer, or you're going to be cleaning it up all the time, which is no easy process. So for tissues, here's the sort of the simple overview of what we might do. And tissues would include things like blood as well. Early on, I was working with people in Sweden, and we were working up the methods for human breast milk, which was a big concern early on. We worked on measuring metabolites in urine, but blood was really what people were interested in measuring as far as human exposure. We do an ion pair extraction with TBA and methylbutyl. Blank. Anyway, MTBE, I'll put it in a minute, sorry. And then we would use a C18 column. We can use a fluoroalkyl pre-column. So I told you your instruments are all going to be contaminated. One of the things you can do is put a column, a short prep column, on the front end. So you're going to inject your sample into that, and then it will separate your sample or your compounds of interest from what get added into the instrument after that. So it just resolves on the chromatography the contamination coming from your instrument from what you're actually putting into the instrument. So it's a pretty simple fix. And then we use electrospray mass spectrometry. People have tried to use QTOF, which is the time of flight instrument. I would not encourage you to do that. If in biochemistry, I don't know if you have QTOF or not, but you can do it, but it's really difficult and a lot of problems. I would not encourage you to do it. I and my students spent years trying to figure out how to do that. One of the reasons and we did come up with methods to do that, but what I wanted to do was the binding of these compounds to human blood proteins, serum albumin primarily. That meant I had to get these small molecules, mass 500 and 499, through the mass spectrometer and through the LC, and I had to get the protein through the LC and the mass spectrometer without destroying that. So that was a real difficult process. The QTOF, the time of flight instrument, allowed me to do that. So for certain applications you can do that, but for routine things that you might be up against, I would not encourage it. Now, I think I have a slide here. I'll go back to those. So to explain the next thing, I have a picture here. So this is a triple quadrupole tandem mass spectrometer. Basically, the way it works is you have a source, that's where your sample comes in, and then you have an initial quadrupole that sort of separates things just based on mass. And then you ionize things. So you have a reaction chamber, you make an ion, because in mass spectrometry we're measuring the mass to charge ratio. You ionize that, but you do it in a soft way. You can do it by electrochemically, is the best way. You can control things best. But you can do electrochemical ionization, you can do chemical ionization, you can do atmospheric pressure ionization, but you want to do something that will ionize the molecule, and in negative ion mass spectrometry we knock off a hydrogen, and that leaves the parent molecule with a net, with a single net, or a single negative charge. Okay, so that's what you do in the Q2, and then you measure that, and then you go to the next and you ionize it again. You break the molecule into pieces. I think I have a picture of that here. So basically, this is how things work. You get your parent ion, you determine its mass, and with an accurate mass, remember I told you, now you know what the elemental content of the parent is, plus a hydrogen. And then you break it again into fragments, which is here, and then we measure all of those fragments. So let's go back up here, where I was talking about this. So for PFAS, which is our example PFAS, the parent ion is 499. That's the mass without one hydrogen. And then the daughter products, there are many, but the most abundant ones are 80, 99, and 130. There might be other ones, and depending on what PFAS you're interested in, you'll have unique, because there are rules about how molecules break apart. Okay, so if you know those rules, in a minute I'll show you how we identify unidentified compounds. But for now, for quantification, you're going to need to pick one of those to quantify. So right now, the score is Professor 1, audience nothing. So, what would be the key characteristic that you might want in choosing the daughter ion to quantify on? What would be the key thing you might want? So if we had a whole bunch of daughter products, and one was maybe 1% of the total, and one was 50%, and one was 30%, which one would you choose? Yes, sir?
The most intensive one.
Close. We would call it intense, because there are a lot of things involved in that.
Highest abundance.
Most abundant. Exactly right. Very good. Thank you. Good job. So now it's audience 1, Professor 1. You're catching up. We picked the most abundant one, right? Because that gives you the greatest sensitivity. But you would also want it to make sure it's unique. Because if it's not unique, you would be quantifying something else. So, I like to tell stories. I think I'll stop here and tell a quick story. So, some of you know one of my colleagues who was my assistant for 7 years, Curran Pakalam Cannon. You know Cannon. Anybody who knows Cannon, he's really prolific and he's really smart. He's a really, really good chemist. And so, after being in my lab and doing these things, and he's the co-author on that very first paper, then my university, I wanted to get him a faculty position, and they said, no, we won't do that. So, he left and got a very good job working at a university in New York City. So anyway, Cannon and one of my other former students, Yamashita Nobu, you know also, really a very smart guy, they decided they were going to do some studies of this new hot chemistry. Everyone was excited, it was new, it was novel, and they really wanted to build their careers. And they had some good friends in China. And so in North America, if I want to do a study, there's a big study goes on called NHANES, which measures a lot of chemicals in human blood, run by the CDC. If I want to do studies with human blood, it's very difficult. The permissions to use human blood and the regulations. Plus, if my people are working with human blood, they need to enter into a blood monitoring program because they might be exposed to diseases like HIV and things like that. So, and that's really difficult and expensive, so I don't really want to do that. Well, these guys went to China, and they could get thousands of samples from hospitals in China with really no regulations at all. So they got all these samples, and they ran them. Remember, both really good chemists, really world-class guys, ran the analysis, and they published a paper. So they thought, isn't this great? And they made a big splash all over the world because the values they were reporting were like 10,000 times greater than anybody else had ever reported. And so the press was going crazy, governments were going crazy, China was going absolutely nuts. And when I saw this paper, I thought there's a problem. And so I started to look at it and work on it. So they were monitoring this ion, 80, because it was the most abundant, gives you the best sensitivity. That's good. It turns out that in human blood, there is a bile acid. So your body makes bile to, it's basically a detergent to move lipids in your body and basically get them out of the blood into the liver where they can be metabolized. And it's a very difficult molecule to make by the body. It's expensive, it takes a lot of energy, and so your body will retain it. So you don't excrete it. It gets used, it gets cycled, it gets separated from the lipid in the liver, and then goes back into circulation and it's used again. This will come up again later when we talk about risk assessments. So they were doing these analyses. What are the odds? It turned out, I told you that these chemicals are fatty acid analogs. They have structures that are similar to fatty acids, similar to cholesterol. These bile acids in human blood, not bird blood, not fish blood, not anything else, only human, had the same mass as PFAS. It had exactly the same LC retention time. It had the same parent ion, 499, and one of its transition ions was 80. Now, because these guys had experience with PFAS, they wanted to use 80 to be sensitive. Now, I looked at this and said, there's really something wrong here. These people should all be dead. They shouldn't have concentrations like this. What's going on? And I just shifted over and I looked at 99 and the blood concentrations went way down. So I contacted Canon and Nobu and told them I think their paper was wrong. I wasn't an author on their paper and they hadn't asked their professor to look at it. And I said, I think your paper's wrong. Now, they're both my friends. The last thing I wanted to do was destroy their careers. So what we decided to do was write a paper on this problem and then use their paper as an example and give the corrected values in the paper. So this worked out pretty well for them because now they got 2 papers instead of 1 and their careers weren't destroyed. But you need to worry about things like this, right? So when I do a quantification, I would look at multiple transition ions, and they better all add up. Even though they're different sensitivities, you should still be able to compare them. And if they don't add up, it means you misidentified your analyte. So here's the analysis for blood. Same kind of thing, and we would do this by matrix matched analysis. That means we would make our standards up in the matrix of interest, and that will take care of interferences that are going to either depress signal or augment signal. Okay, so matrix matched analysis, and we would be using internal standards for isotope dilution, and we would also be using other standards for recovery, so to make sure we have recovery. But you can do this pretty straightforward. Here's ion pairing. I'm not going to go through the specifics here. If you're interested in doing this, it's all in the SOP. But basically what we do is we pair, I call it ion pairing because we're going to pair the ion of interest our PFAS or PFOA with an extractant, and then extract that, and then do that analysis. So we're going to pair it with TBHAS, and then partition that into MTBE, methyl terbutyl ether. So like I said, you know, the SOP for doing this is maybe 20 pages long. So there are a lot of little things that you need to know how to do. Here's just some information on mass spectrometers that will work. This would be the one I would suggest if you had the option to buy that. And then you can use mass links for the analysis, the instrumental analysis calculations. You can use a triple quadruple tandem mass spectrometer if you have one available. The SciX equivalent of the 4000 will work. You can do these analyses. The detection limit and mass resolution. Mass resolution is not all that important if you're focused on one chemical. Like if someone says, I'm going to do PFAS, but if you're looking for all of the PFAS, now mass resolution becomes critical because they're similar structures, which means they're going to have similar retention times and they may have similar ions. So you're going to want as much resolution as you can get. And my instruments are conservatively have a mass resolution of 2 parts per million. So about 1 times 10 to the 6th, 1 over 1 times 10 to the 6th atomic mass units. So that's sort of what you need to get into this business. I showed you the mass spectrometers. There's a picture of one. They're the size of your car and cost more than your house. So that's how mass. So how do we quantify? I've talked a little bit about this already. Some people would use only retention time. And so historically, and there were some talks at the meeting here, where people were using retention time, and they were actually coming up with models. The group in Spain does a lot of work with trying to predict retention times for unknown chemicals because they're going to use that for identification. I would never, ever use retention time to identify PFAS. So bottom line, don't do it. In our library, which I'll show you in a minute, one of the things that's in there that helps you in trying to decide what a chemical is retention time. It's a starting place, but it's not what you want to quantify on. So we have our parent ions, the primary ion. You can do in positive or negative mode. For unknown chemicals, I will routinely run the same sample in positive and negative mode. You sometimes get the same thing, sometimes you get things that are a little bit different. But for quantification, for most PFAS, negative ionization is the best way to go. The problem that can inhabit blood, you generally pick the most abundant, but make sure it's not going to give you an interference. So I talked about this too, this matrix effects. So we're always going to want to do matrix matched analyses. That just eliminates those problems. And then you use internal standards. You never ever want to compare your results, say in blood, with an external standard in methanol. One of my papers goes through all the math about why this is a problem. The one by Doring and Giesy goes through all of the calculations and everything as to how you would do that. But you don't want to compare to an external standard, which a lot of people do. Okay, so let's just look at what we would get in the analysis. So down here are retention times. These are the different compounds of interest. So here's our example today. Our PFAS, and then here's 99 and 80. So we use both. It seems to be that this was correct because 80 is in the same place. So this molecule is giving us both of those transition ions. So we can check that. Here's an example in water, the kind of analysis that we would get. And read out in abundance. Here's another one, a spiked water sample. So here's, we've spiked with individual chemicals, and you can see here's the spike, here's our background. So the key thing here is that our spike, or our chemical of interest, is well resolved from the background. It's not always the case. If your spiked peak is way down here in the noise of the instrument, then you won't be able to detect that. Okay, mass spectrometry libraries. Anybody been to the mass spec library? I think it's over here on the corner. Oh no, it's not that kind of library. Sorry. It's not a bibliothèque. How do you say it in Serbian? Bibliothèque. You stole it from French. I speak French. Okay, so what we're going to talk about here is a library that you can use to help you identify a chemical. So when you do your analysis, you're going to have a retention time for a peak, and you're going to know if it was positive or negative mode that you ionized it, and you're going to have a mass for that parent ion, and you're going to have your transition ions. And with that information, you should be able to identify the compound. Now, if you're nuts, like me, my wife will tell you when I was a graduate student, way back when computers weren't as well developed as they are now, I would sit around memorizing all of that information. I had it all here. So I could look at a fragment pattern and pretty much tell you what it is. Nowadays, none of you will be able to do that. And I would not encourage you to do that. It's a complete waste of brain power, because you can look it all up, right? You can search on it and look it up. So don't do that. So here's what it might look like. And this is how I got the instruments cheap, because I had a whole bunch of mass libraries that I gave to Thermo and said, you can sell it. You can sell it to people and make money. Just give me a good deal on instruments. So in the library, here you're going to have a retention time. So if you've analyzed something and you know what your retention time is, and often we'll run standard chemicals to calibrate our instrument for retention time. So you know that on your column in your instrument, when you get a retention time, it's the same I might get or Flavia might get. Okay, so you need to make sure you've calibrated your instrument so your retention times are accurate. We have retention times generally to 1/100th of a minute, and so they're here. And so you know your retention time, so you might go to the library. You can search all this automatically on the computer because it's all in the spreadsheet. And then it would come up and it would give you different intensities for these different ions. And then this would be the mass to charge ratio. And so this would be 248.9796. Now, off your instrument, you would get one more decimal place, okay? But you need one decimal place for rounding, always. So I would only report 4 or 5. I'm happy with 4. Some people would report 5. The instrument will give you 6. But with 4 decimals, positions beyond the decimal, you can get an accurate mass and that will give you the formula. Okay, so now we can probably identify the chemical. Now, how many chemicals might have that retention time and that formula? Or how many chemicals might have that formula? Any ideas?
Too many.
Give me a range.
Too many.
No, that's not an answer. But just as an idea, why don't you take a guess? No, you're on the right track.
Oh. I don't know, 50 maybe.
That's not a bad answer. You pass it back to her. There you go. Yeah, no, that's a good answer. Yeah, routinely, we would get maybe 30 chemicals that have the same formula. Now, what we don't know is how they're put together, right? We don't know what the structure is. Okay, well, let's talk about that. How might we do that? Just a little bit. You always want to report accuracy and precision. I got a few more of these. What's the difference between accuracy and precision? You already got one. We're going to give somebody else a chance first. You'll become teacher's pet. Anybody else before she wins another one? Yes, sir.
Accuracy is how close you actually to the value, and precision is how these squares are your.
Very good. Yeah. The key point I want to make that he made for me is accuracy and precision are different. Okay? And you have to report both. And accuracy is often the most important. That's how close you are to the real value. And then the precision is not quite what he said, but it's how much you could reproduce it. It's determined by how variable it is run. But so for us, precision would be we might run the sample 5 or 6 times, and we want to know really what that value is. And we generally like it to be, maybe 5% or less. Over time, the standards and the instrument changes. We call it instrument drift. So we would run lots of samples. We might run 5 samples, and then we clean, we would run salt in between and things, and then we would run a standard. We would develop a standard curve, but then through the process we might only run one standard to make sure that we were still accurate, that we were still close to the right value. And then for these, in water, our detection limits around 15 parts per trillion. And as I told you now, in the United States, their water standard is dependent on what's detected. So if this number goes down, that means the number that a drinking water treatment plant operator needs to meet will go down. Okay, so there are a lot of chemicals out there, I think. Oops, sorry. I thought I had a slide here. I think right now there are about identified PFAS about 1,900 known. They're not all in the environment, but some are found in industrial processes and things. But about 1,900. How many of those do you think there are standards for? All of them? No, not a chance, right? Just a few. The standards are somewhere in the range, it's changing all the time, but somewhere around 50 or less of all of those. So that means most of them we don't have standards for. Without a standard, we don't know exactly, without what we call an authentic standard, we don't have a retention time, we don't have an accurate mass, and we don't have a fragment pattern to compare to. So what do we do? Well, I told you, with our resolution, we get the the formula. We know the formula. And there are rules for fragmentation, and you can look those up. There are some good books about how to do it. But once you know that fragmentation pattern, then you can determine really what the molecule is. A key point is that mass spectrometry, as powerful as it is, will not give you stereoisomers. It will not allow you to identify optical isomers. Okay? We can get structural isomers. So if a fragment is in a different place, I can find that and I can identify that. But if you have something that has an optical isomer, we can't determine that by mass spectrometry. Toxicologically, that's important. There are a lot of examples of drugs. A lot of the drugs that you might take on a routine basis, like acetaminophen, what's it called in Europe? Anyway, has optical isomers. What you buy is what's called a racemic mix. It's some of both, but only some of them are active. I take a drug for other reasons that is very expensive because one, the R version of it is potent and the L not, so they actually separate it before they sell it to you. So optical isomers can be very, very important toxicologically. The mass spectrometer won't tell you. You won't know. Things will be there as a mix. I just finished working up a whole assessment on a new insecticide that's safer for bees called sulfoxaflor, if you ever read about it, but it's now registered. And it has some optical isomers, and it has some structural isomers, so we had to work through those issues. But anyway, key thing to remember, it's not that it's not important, but you can't determine it by mass spectrometry. And then there are often multiple structures for a particular mass, and we try to determine the structures by using these mass spec libraries of fragments. So isotopes of fluorine we need to talk about for a minute. Fluorine has 19 known isotopes, ranging from 13 to 26. But in the environment, naturally, there is only one isotope. So often when I'm trying to identify things like brominated compounds, bromine has 3 stable isotopes in the environment. I can use that to help me identify what the chemical is, because that will allow me to determine how many bromines are in the chemical and things. But for fluorine, we can't do that. So fluorine is monoisotopic, and it has only the one natural stable isotope. All these other ones are made in various chemical processes. Okay, so we developed a technique we call typic frag, which again I gave to Thermo to market, so you can buy it. They don't call it that. So real quickly, how I would identify a compound, and this is not a fluorinated compound. I just put this slide in recently, and I didn't have the stuff that I needed. So anyway, this is an example of an azo dye that we identified. Actually, this was pretty controversial because I identified the structure and had a big fight in the literature because there were no authentic standards, and a group in South America was questioning us. Anyway, we worked it all out, and in the end I was right. So that was good. But anyway, long story short here, don't pay any attention to these isotopic things. But we would get what we call our precursor ion. This is our parent ion. And for PFAS, this would be 99. And then we have our elution profile, so we have our retention time. And then up here, we would have all of the different mass fragments. And then I know what the formula is, and then based on the fragmentation pattern, I can come up with a structure. You would like to have an authentic standard to compare to, right? Without it, you can publish sometimes, but people are going to question you. Because for these, like for this particular one, for this brominated compound, there were 30 possible structures for that formula. So we were able to figure it out. To do this on the mass spectrometer, we use data-independent acquisition and mass spectrometry. So what this will allow me to do is not focus on a single PFAS. But if I know I just want to look for PFOA or PFOS or something, I wouldn't do this. But because the limitations of the mass spectrometer, so the resolution is determined in part by how quickly the mass spectrometer can cycle, right? So when every time it makes a measurement, and it's in nanoseconds. And the reason we get better resolution with an Orbitrap is that resolution time, or that duration between readings, is shorter, smaller. In most mass spectrometers, if you don't have, particularly if you don't have an Orbitrap, what you do is you can run a whole bunch of windows. So you set up a whole bunch of mass windows, which allows you to have more residence time on each mass within that window. So normally, we would, if you wanted to run all the way from 0 to mass 1,000, for instance, that would mean that for each of the masses in there, your residence time or dwell time would be 1/1000th. If we break it up into windows, that means that our residence time on each of the masses can be longer. So that's what we do. Normally for PFAS type things, with my instruments, we would put 5 or 6 of these windows. So for each chemical, then we'd be collecting the mass data over the range within each of those windows. Gives us greater resolution, gives us better accuracy and precision and detection limit, but we have to basically run the sample a number of times. Okay, so that's what that's all about. In the SOPs that I'm giving you, there are a bunch of things like this. I'm not going to go through it all here today, but when you look at them, this is for bromine. It's one I had here when I made this the other day. It'll have flowcharts in there. It's step by step what you do, how you extract it, there are different SOPs for extraction and instrumental analysis and quantification. Anyway, just follow the flow diagram. It will tell you exactly how to do it. And I just threw these in as just some examples of real samples and real formula calculations. And this is where I was identifying all these brominated compounds. Just as an interest, there was a big controversy with a friend of mine in Sweden called Åke Bergman, and he had measured some analyses of marine organisms and concluded that there were very, very, very high concentrations of brominated flame retardants, your favorite thing, right? And this caused a big stir, and I looked at this and said, well, that's crazy. I knew how much brominated flame retardants had been manufactured, and when I did a few calculations, there was no way they would account for the organobromine in marine organisms. Anyway, we worked it all out, and it turned out his idea was that they were methylated in organisms, and these were degradation products of brominated flame retardants. It turned out they were natural products. And so, anyway, it was a big controversy. A lot of people yelling and screaming in the literature. But again, I was right. These are just some, extracts of different things. So this is, here's the PFAS, mink liver. The key thing here is it's pretty clean. It was one of the few pieces that we found. Here's some amphipods. Here's PFAS again. And I was comparing between solid phase extraction and non-solid phase extraction. Here's some blood serum. Here's our PFOA. So with our detection limit and our limits of quantification. There's more analyses. Here are R squareds for our matrix matched standards. Relative standard deviations, I want it to be less than 5%. Here's one that's above 5. But normally the relative standard deviation down around 2, PFAS anyway. Blood samples, here's some of our recoveries. So you do need to calculate recoveries. Here's one spike. So here's PFAS, essentially quantitative recovery, 84%. So those are the kinds of things you want to be able to report, accuracy and precision. I told you this story. This is the paper that they published that was wrong. I told you this whole story, the biases in human blood. So this was a big deal because people really were worried. So I told you that story. So this is the paper I published with Canon that corrected this problem. So this paper explains all these things in here that I told you about before, but it has the details of what the bile acids were and things. And conclusions on human blood. We've done lots of studies with lots of different things. Found lots of different PFAS. I want to get to more recoveries. I have one last thing I want to talk about. Okay, so the last thing I want to talk about in this section before we move on to, what do you do next?
Make a short break. You need to take the rest.
Yeah, after this,
Coffee
I'll stop,
Yeah.
take a break. But what's the next one we're doing? Is it
Environmental forensics.
forensics? Okay, we'll do that next. I told you that there are no useful isotopes of fluorine. We can use NMR. So you would extract your sample, isolate the organic material, and then quantify how much fluorine is there. You can use NMR, but it's not very sensitive. So you really have to concentrate your sample a lot. One of the things that I would routinely do, say with bromine, is use neutron activation. Neutron activation, you put your sample into a neutron flux, a reactor. We have one on our campus, so we put a sample in there, irradiated, and through an N-gamma reaction, it will absorb a neutron, and then in its decay, will release a gamma ray, or a beta particle, or an alpha particle, but we measure the gamma rays. That's very, very accurate. You can't do that with fluorine. Okay? There is the fluorine won't absorb a neutron and make a radioactive compound that has a half-life long enough for me to make a measurement. Okay, things happen, but they decay in nanoseconds. So theoretically, you can look them up that they were deformed, but for me to be able to get the sample out and extract, do the things I have to do to measure it, I can't do it. So you can't use neutron activation. So what do? I'm going to move that off of here for a minute because I've got one more here, another one. So what might we use for quantifying total organically bound fluorine? Remember, I'm going to use this in a mass balance. I'm going to measure all my chemicals, figure out the mass of fluorine associated with all those, and then compare it to the total to determine what proportion I quantified or identified. What might I use? Any ideas? Oh, wow. Catching up, Professor. 2. Audience. Yeah, 3. You're still ahead. You're doing well. Okay. What we would use is something called combustion ion chromatography. So we would take our sample, say a blood sample, I dry it, and I put it into a combustion chamber and put oxygen in there, burn it, and then go through an ion, a trap, sodium chloride or potassium chloride, trap that, and then I would put that into an ion chromatograph. And then I could quantify the amount of fluorine, and I would know that it was with organics because I had specifically extracted organic compounds. So, a little more, I told you all that. Yeah, so this was a new term for me when I was looking at the half-lives of some of these isotopes. They're in yoctoseconds. Anybody know what a yoctosecond is? It is 1/1,000,000,000 of a trillionth of a second. Oh my God. So, not very long. But I learned something. So, last thing to show, I lived a lot of my life in Hong Kong and worked with colleagues there. And here's some things that we did with PFAS. One of my students there, Henry Yip, just published a paper, I think last week, or the week before, and it's in the ESFT, it may not even be out yet, but it was accepted and ready in some of the marine mammals of the Pearl River Delta. But here, we can measure all these different, and here's a list of, this list generally makes up about 95+% of the compounds, and then we can determine the proportions that are in different things, and then we can calculate the total and measure this organically non-fluorine to determine. And in this case, in these samples, we were identifying 99+% of all the perfluorinated compounds that were there. So here's how we would do those calculations, and here's some of our different animals. So we measure all these different compounds, get the total, and then we would compare it to the organic extractable. And you'd like to do this if you have novel samples. You'd like to know what proportion of the organic non-fluorine you would have. So real quick, for PFAS and PFOA, I like to say catastrophe was avoided, but not by much. And there's still ongoing problems, as I'll show you tomorrow when we go through a whole risk assessment. I'll go through a whole global risk assessment from A to Z and show you what the situation is. It's not catastrophic, but it's still not good. We're exceeding no effect levels a lot of places for a lot of species. Concentrations are decreasing. In the toxicology section, I'll explain to you again, but the problem in humans is that it's hard to get rid of these compounds. because of this, what we call interhepatic recirculation. Remember the problem with our bile acids. So your body tries to get rid of these chemicals, and the body says, oh no, not that, it's bile acid, it's valuable, keep it, and grabs it and pulls it back. So we'll talk more about that later. And so I work a lot in Canada with our Minister of the Environment, and we now have 87 individual PFAS chemicals banned in Canada. A lot of these are still made in China, which is an issue I'm working on, and with that I'll stop. Field any questions you have. I know I can't give you all the details. You need to go into the lab and do these analyses, so I'm sorry for that. My goal today was to just make you aware of some things so that later, even if you're not doing the analyses, if you've contracted with a laboratory like Lata maybe, or laboratory to do it, if you've contracted with a laboratory, at least you know what to watch for, or what to talk to them about, or what to ask them about, to make sure you're getting accurate results. Okay? If you want to do these analyses, the best thing to do is contact me. Look at the SOPs I'm leaving. Just contact me, email, and maybe we can do a video conference or something, and I can get you started. But the key thing is you're going to need that valuable instrumentation. If you don't have it, please, please, please do not try to do these analyses. You'll just make mistakes. Okay, that's it.